Hi, this is Lecture 3 for MEC 3820, Heat Transfer for the summer of 2020. Where we're going to begin is speaking about the first law of thermodynamics and making clear that what we're essentially talking about when we talk about the first law of thermodynamics is a form of conservation of energy. Now, the first law can be applied to both an open and a closed system, but for our purposes at the time being, we're going to consider a closed system. So a closed system is a certain amount of mass. It can be some type of fluid, gas or liquid, or a solid. And again, for the first at least 1/3 of this class, we'll be dealing with solids in terms of conduction. So we can think of this as a boundary that encompasses a certain amount of solid mass. And that boundary that boundary around a certain set of and that boundary enclosing a set volume So this closed system, which has a boundary that encloses a set amount of mass, can be considered as a thermal reservoir, meaning that that mass will have a certain amount of thermal energy at its constant temperature. So in this case, we'll look at the stored energy as being equal to the total amount of mass times its temperature times its specific heat. Now notice I'm using the term C sub P here, but when we're dealing specifically with a solid, this specific heat will just be C, right? There isn't a different specific heat in terms of pressure and volume for solids. It's just the specific heat. And in this case, the temperature is going to be with respect to absolute zero. So this would give me the total amount of stored energy within the system. Now, but most of the times we're going to be looking at are going to be changes in the amount of stored energy or changes in the amount of energy going into or out of a control volume. And in that case, we'll be dealing with delta T's. All right, so again, we take this closed system, we have the total amount of energy within the system, and then we can do work on it. So we can do PDV work, which takes into account the fact that the boundary can move in and out. Again, for a solid, we won't be dealing with PDV work, but it is present. And same thing, we can do shaft work. So we can either put energy into this control volume, or we can take energy out by some mechanical means. And lastly, we can change the amount of energy within the system by either putting in or taking out what we're going to refer to as direct thermal energy. And this is the statement of the first law of thermodynamics, that the change in the stored energy within a control volume is equal to Q minus W. Now, again, I'm leaving that up to you because it is in your textbook. Why is this a negative sign? I mean, it's a statement of the first law of thermodynamics. So what we're obviously stating is that there's a direction here with regards to what's positive and what's negative. So I'd like you to go ahead and look that up. But now for our systems, and specifically for heat transfer, we're really not going to be dealing with the work terms. We're not going to be dealing with PDV or shaft work. So we're really talking about thermal energy. So in this particular case, what the diagram is showing here is essentially a volume. In this case, I've made it a rectangle, and there's two things that can be happening within the volume. We can have stored energy and energy generated. Now note, I've changed most of the terms later on in these slides, but these two terms are going to be slightly different in your textbook. I think this is E of the element. I think it's E element, and this will have a little e dot, little e subscript gen, so energy generated. So in this case, we can allow for energy to pass into our system from either side. Right? It's a control volume encompasses in total mass, or we can have energy moving out. So in this situation, our first law can be the change in the stored energy in the system will be E in, right? That's going to be a positive change in stored energy minus the energy leaving, which would be a negative amount, plus whatever energy is generated within the volume itself. And we'll come back to, and the book actually gives a nice explanation as what we're referring to, what things can be used to generate energy within the volume. And again, we're going to be talking about, in terms of heat transfer, mostly a rate situation. So in this case, we're going to be looking at the time derivatives, or essentially the per unit time basis. So the rate of change of the stored energy within this control volume will be equal to the rate at which energy enters the control volume minus what the rate of energy that leaves it, and to that we would also add in whatever energy may or may not be generated in the control volume per unit time. So in a lot of the analysis that we'll be doing coming up, we'll be talking about what's referred to as a surface energy balance. And really what we're talking about is the smallest form of a control volume that you can have. I'm going to call it a degenerate form of a control volume because it's essentially, it has no volume. Where you take the sides of the control volume and let them squish in until there is only an input side and an output side, but the surface, those surfaces don't encompass any volume. So again, it's a thought experiment, but it allows us to discuss what's happening directly at the surface of a control volume. And then, since this control volume doesn't have any mass inside of it, there is going to be no stored energy or no generated energy within that control volume. And what we're going to be able to do is apply the conservation of energy, or the first law, to this surface volume, the surface control volume. So that's what I have here. We're looking at the first law that we generated 2 slides ago, but these two terms, they're zero, they're not present. So if I rearrange this is essentially what you'd get. The amount of energy passing into this surface control volume has to balance or be equal to that which is passing out of it, because there's no mechanism for the energy to be stored. All right, so in writing it this way, if this was a solid and say this is a fluid or a vacuum out here, well, it has to be a fluid because I'm dealing with convection. So what we're essentially saying, if this is one particular scenario, that we can have the energy transferred from the solid into the surface and then out of the surface via the 2 possible mechanisms of heat transfer that we have, either radiation or convection. And what we would do in this particular case, we would say that anything's coming in is positive. So here's my Q dot conduction, this is my E in, and these 2 terms are my out terms. So minus Q convection minus Q radiation, and that has to equal 0. I'm not sure why I have that C there. That's not right. So little mistake on my slide, which I'll fix up at some later point in time. Anyway, so in this case, we'll looking at the more general case in such that we would allow that the radiation can be into or out of that surface. Same thing with convection, same thing for conduction. So we would know that if we have a high temperature surface out here and the gas that's flowing over it is hotter than the solid, than the temperature of the surface of the solid, that everything would be flowing to the right. So a more general way of writing the surface energy balance is to leave all the terms positive. So, and then obviously for this to equal 0, again, I don't know why that C is there, which I'll fix again at a later point in time. Each of these terms can either be positive or negative, such that the sum of all 3 of them would have to equal 0. All right, so let's look at a quick example. So in this one, we're looking at the thickness, we're trying to determine the thickness of a masonry wall, and we're given the thermal conductivity of that wall, and then we're saying we want to know what the thickness of that wall has to be if it has to be 80% of the heat rate through a composite structural wall that has a different thermal conductivity and a specified thickness. So we're essentially saying both walls are subject to the same surface temperature. So this is a design study. We're essentially saying, all right, this wall over here, the masonry wall, has a set thermal conductivity. This structural composite wall has another thermal conductivity. And we are looking for the amount of energy flowing through by conduction through the masonry wall and through the composite wall such that these two are associated by each other by this simple equation. The heat rate through the masonry wall has to be equal to 0.8 times the heat rate through the composite wall. And what we're saying is that the temperature, or the driving force that's going to allow this energy transfer, this thermal energy transfer to happen, is the same on both walls. So this is basically our governing equation, and now we essentially say, well, we're having conduction through a solid wall, so the way heat transfer would occur is through conduction, which can be described by Fourier's law. So Fourier's law is minus K delta T over the total thickness, in this case the thickness of the masonry wall and the thickness of the composite wall. And what I've done here is the left-hand side is for the masonry wall, the right-hand side is for the composite wall, which I'm multiplying by 0.8. So in this case, the negative signs go away, they cancel out. The delta T's cancel out. So what we're left with is essentially a bit of algebra to do, and we find out that the thickness, the required thickness for the masonry wall is 375 millimeters, such that they both have the same heat transfer rate. So here's a second example, and this one is an example using convection. So in this case, we're looking at essentially putting your hand out the window to cool it off if you're in a car, or if on a very hot day you're by a nice stream of water and you want to put your hand in the water and see what happens. All right, so it's actually not a very warm day because it's at -5 degrees, but never mind. All right, so what do we have here? The surface of our hand, the temperature is typically 30 degrees, so we're looking for convective heat fluxes for two situations. A vehicle, when we stick our hand out into a airflow that's at 35 kilometers an hour, right, because we're sticking our hand out the window, and that would induce, right, depending on your frame of reference, either the car is moving at 35 miles an hour or the wind is blowing past you at 35 kilometers an hour, and the air is -5 degrees. And they give us a convection coefficient. So under these conditions, the convection coefficient is 40 watts per meter squared per Kelvin. And the other situation is, what if I put my hand in a stream and the stream is flowing by at a velocity, right? So we could combine that into a volumetric flow rate if I happen to know the total air cross-sectional area of the river. But in this case, we know the velocity, 0.2 meters per second, and the stream is 10 degrees. And then they tell us that there's a much larger convection coefficient here. And they're saying which condition would feel colder. Now I want to point out to you that this is extra information. The 35 kilometers an hour and the 0.2 meters per second are both information. Those relate to these convection coefficients. So 35 kilometers an hour in air is going to produce a 40 watt per meter squared per Kelvin heat transfer coefficient. And same thing, 0.2 meters per second in water is going to produce this 900 watts per meter squared per Kelvin. And that's going to be the second portion of our class, the convection. We're essentially going to be figuring out how we develop those convection coefficients. But for now, they're given to us. So this is essentially a listing of our givens. So we have an H and a T infinity for each condition. We're looking for the heat rate coming out of the surface. So I have it as listed as Q dot here. Just wanted to make sure that we have both of our terms. So Q dot would be the flux. So this would be Q dot, capital Q dot, which is watts, and watts divided by some surface area would give me the small Q dot, which is watts per meter squared. And we're saying that for both cases, the surface temperature of our hand is 30 degrees. So we list our information for our two cases here, and we want to vary or take a look at both of these cases given to the last sentence here in the problem statement is contrast these results with the heat loss of approximately 30 watts per square meter under normal conditions. So your hand is at 30 degrees Celsius, but also typically loses 30 watts per square meter under normal conditions. So for case A, we're given H and we're given our temperature difference. So in this case, the airflow is at -5 degrees C. So right, we know it, right? the hand is at 30 degrees, the water stream is at -5 degrees, or the air stream is -5 degrees. So that's a 35-degree difference. But just be careful when you do your algebra. So in this case, it's 30 minus the -5 degrees. So that gives you a total temperature difference of 35 degrees. And 35 times 40 gives me 1400 watts per square meter. Right? There's no A here, which is why we're dealing with the heat flux on this side. Case B is the water's flowing at 10 degrees. So we have Q dot equals H Ts minus T infinity. So H, the heat convection coefficient, is 900 watts per meter squared per Kelvin. Multiply that by the temperature difference, right? We know it's 20 degrees, but again, doing the math, it's 30 minus 10. And notice I have Kelvin over here, right? It doesn't matter if it's Kelvin. It doesn't matter if it's degrees centigrade, right? It's a temperature difference. So, but in this case, I'm explicitly writing Kelvin here because I want to show that it cancels with your heat transfer coefficient. But again, it's very, very important for you to remember that since we're dealing with a delta T, the degree Celsius and the degree Kelvin are the same quantity. So they both would cancel, whether this was degrees centigrade or degrees Kelvin. And what we end up here is that the heat loss, putting our hand in a stream, is 18,000 watts per meter squared. So the airflow, 14,000 watts per meter squared. A much larger heat loss, if I'm putting my hand in cold water, 18,000 watts per square meter. And obviously, both of these are quite a bit larger than the 30 watts per square meter that my hand would feel just in a regular environment. Right. All right, so with this example, I'm concluding our discussion on Chapter 1 of the textbook. So we've done a couple of examples. We didn't do any radiation examples, but that's okay. It just gives you this idea of how we're defining heat rates and our couple quantities that we want to keep straight in our head, and how the first law of thermodynamics relates to it. And explicitly, the second law of thermodynamics is related to all of this by the fact that energy is going to flow downhill. Regions of high temperature, which have a lot of thermal energy, are going to transfer that high thermal energy to lower temperature regions, which have a lower thermal energy. So energy will run downhill.